FA. So here it is. Now there's quite a few details there, and you can construct this transition table, because it's obviously a table, right, with rows and columns, and sort of like a matrix. So it's a table, and here are your next states, or a set of next states, because so your transition function here, the right hand side, PQ, that's a power set, right? Now what is a power set? It's the set of all subsets. So it's like a set of sets. So an element of a power set is a set. Okay? So on the right hand side here of your delta, your transition function, your delta, so you will have sets. You'll have sets here, right? Because they're elements of the power set. So that makes sense. All right. So well, let's do a. I'll get out of the picture. You just hear my voice a bit because I need both. All right. So Q1, you're in state Q1, and a 0 comes in. So you deterministically you loop back to Q1. Okay, so you're in Q1, a 0 comes in, so you go to Q1. But it'll be a set of Q1. And the Q1 is the single member of the set. Okay, so Q1 as a set here. Okay, so now if you're in Q1 and a 1 comes in, well, you've got two exit transition arrows with a 1. So that's non-deterministic. So you can go. So your set of next states will be. You can loop back to Q1, or you can go to Q2. Right. So that's there for 1. Now Q1 and eta. How does that work? Because now with an eta, you don't wait. Remember, it's a bit tricky with the eta. You don't wait to read the next input symbol. You just you make the transition immediately. And so let's see what happens then. So for Q1 and you've got an eta here. So the Q1 sort of disappears because is it right? It's because it's your Q2. You get a copy made, and one machine goes into state Q2 and the other one goes into state Q3. I think that's correct. I'm still a little fuzzy on the use of eta. Hope you're following it. Anyway, the beauty of the full definition is that it allows you to disambiguate. So by studying this table, you hopefully can deduce answers to the question of like how does eta function in detail, because it's here, right? It's all the full details of how the transition function works is in the table. Okay. Okay, so how about Q2 and 0? Why does it go to Q3? So Q2 and a 0 goes to Q3 deterministically. Okay, so that's okay. Now Q2 and a 1, what happens? Well, there's no 1 coming out, so Q2 just dies. So that would correspond to this. Right? There is no next state, right? It just dies. So it's the empty set, right? Which is just this. Q2 eta. So if you have an eta, you go to Q3, which gives you that, and so on. Okay, so study that. I suggest also have a good look at the text on Sipser's explanation of how to use eta, because I found it rather tricky. Right, so here, oh, and yeah, the Q1's the start state, because you're starting here. So, here's your starting arrow. So you start Q1, and the formal definition where Q0. So Q0 is Q1. The start state is Q1. So you just put Q1 here instead of Q0. And F, that's the set of accept states. Well, there's only one, so just put set Q4. Right. So there's your formal description of an NFA. The first one we've done. Now, what about? Now, similarly, we did the formal description of a computation. Going through state after state. How do you do the same thing for an NFA? We've done it before for a DFA, the deterministic FA. So how do you do it for an NFA, non-deterministic? All right. How do you define a computation? Well, again, it's pretty similar. So let the NFA that you're talking about be written in a formal description this way. The usual 5 tuple, these 5 things. Okay, and let the input string to this machine, this automaton, this NFA. Let that input string be W. Okay, and it uses symbols defined that belong to an alphabet, capital sigma, right? And a computation occurs, meaning that this machine, this NFA, this N, accepts this string W if, here's things where we get somewhat abstract, pure maths like, okay? If you can write your W as a series, a sequence of these, what do we call them? Can't really call them symbols, because these Y's here, they belong to the augmented sigma, so sigma eta. So one or more of the, 0 or more of these Y's could be the eta. Okay, so if W is defined as a sequence, a string, if you like, of these Y's, and Y is a member, for each Y, it's a member of this set. And what is this set? Well, it's either an input symbol, from this alphabet, or it's an eta. Okay, because it's these are members of this set, and this is the augmented set of that one. So this one is that with an extra element, and that's the empty string, the eta, right? And it goes through, at the end of the session, but so it goes through a sequence of states. I'll just read it out and then come back to it. So reasons of continuity. So it goes through a sequence of states, machine, R0, R1, R2, ... Rm, suffix m. Okay, and you place 3 conditions on those R's, and you'll do the details in the next session.